And later I hope we have seen what is a bipartite graph. Let's say if you have a graph given v comma v e, and then we define what is a bipartite graph. So what is a bipartite graph? We say a graph is a bipartite graph if the entire vertex set can be partitioned into two subsets v1 and v2. Partition, it means v1 intersection v2 must be empty, disjoint sets, right? So that you take any edge of the graph, you take any edge of this graph, okay, which connects a vertex in v1. If it connects two vertices, definitely one will stay in v1 and other one stays in v2. And also we do not find any edge between two vertices of v1. Similarly, two vertices of v2. If there is an edge, definitely that must connect a vertex in v1 and a vertex in v2. Then we say such a graph is bipartite graph. I hope we have seen some example, right? For example, if I take this graph, yeah, we define what is a complete graph. Yeah, this is K3, right? So this is a cycle also. It acts as both. So now this is K3. Now I have a question. Is K3 a bipartite graph? Is K3 a bipartite graph? No. Let me take C4. It's a cycle with 4 vertices. Right. Now, is this a bipartite graph? Is this bipartite? Yes. Okay. Now let me do one thing. Let me name the vertices 1, 2, 3, 4. All right. Now what is the partition you're taking? Here the vertex set is 1, 2, 3, 4. All right. Now how do you say that this is bipartite? Like what are the vertex subsets you are taking? What is v1 and v2? Yeah, you say that v1 is 1, 2 and v2 is 3, 4. Right? You can redraw this graph like this. I mean, you can keep 1 here and you can keep 2 here. Oh my god, I gave numbering. All right. Anyway, so it doesn't matter how you represent those vertices. Okay, that's fine. Let me keep that. So here 1, 2. Here I'm taking 3, 4. All right. Now we can connect this, right? So how do you connect? 1 is adjacent to 3 and 1 is adjacent to 4. And similarly 2 is adjacent to 3 and 2 is adjacent to 4. Yeah, this way you can see. Right now the first set is v1, that is 1, 2, and the second set having 3, 4. So it is very clear that this graph is bipartite. All right. Now there is one important theorem. Using that we can easily identify whether the graph is bipartite or not. Okay. Now what it says is, see, whenever the graph is bipartite, what we can do? We can actually divide the entire vertex set into two subsets. Okay. And one subset you can write it on one side, right? And other set you can write it on another side. And now if you have edges, definitely we are going to have an edge between like these guys only. We are very sure that this, what is it, the color I used here, this blue color one is not connected to blue color one again. Okay, if there is connection, a blue color one will be connected to a red color vertex here. It is not that the vertices of same color will be connected. Okay, after making the partition, I'm coloring the vertices in v1 with blue color and in v2 with red color, right? Now if I look at the original graph, let us say this is the bipartite graph initially, sorry, after separating it. But when you look at the original graph, they may not be arranged like this. Okay, I hope. Okay, let me take an example. I'm taking C6. Is C6 bipartite? Let me give numbering here. This is vertex 1, 2, 3, 4, 5, and 6. So is it a bipartite graph? Alright, so you're saying that this is bipartite because uh, here, what is the set V1? If you look at the vertices which do not have connections, like 1 and 5 do not have direct connection. Let me keep it here. And similarly 5 and 3 do not have connection. Yeah. Now I cannot take 2 because you may say that 5 and 2 are not connected, but the thing is, since I have three here, I'm not allowed to keep 2, right? So that's it. The set got closed. Now let me take V2. What is V2? That is 1. Okay, 1 I have already taken there. So 6, 4, 2. Alright. So now if I redraw this graph, what is it? I'm taking 1, 5, 3 here. This is 1, 5, 1, 3, 5. And similarly here, let me take 6, 4, 2. Yeah. Now let us establish the connections. 1 is connected to 6 and 1 is connected to what else? 2. Then and 3 is connected to 4 and 3 is connected to 2 as well. Right. And 5 is connected to 4 and 5 is connected to 6. Alright. So now you see that I am coloring V1 with blue and V2 with green. So here what we can say is, if the graph is bipartite, you can assign one of the two different colors to each vertex. Okay, you fix with two colors. Okay, you take two colors, either green or blue or red, anything. Okay, you can assign exactly one of the two colors to each vertex so that no two adjacent vertices are having the same color. For example, here the vertex 1 I am assigning blue color. Okay, then the adjacent vertices should not be assigned blue color now. They should be assigned other color, that is green. Okay, let me assign green here, green here. Okay, and here when it comes to 5, what is the color we are going to assign? We are not allowed to assign green because if we assign green, now adjacent vertices are having the same color, right? So I'm not allowed to assign green here. Let me assign blue, right? Here let me assign blue, right? Just a minute. So finally the vertex 4 can be assigned green color. Now you see we colored the vertices of the graph with two colors so that no two adjacent vertices having the same color. Okay, so that is what the theorem says. So the theorem says that if a graph is bipartite, if and only if the vertices of the graph can be assigned with one of the two colors so that no two adjacent vertices are having the same color. Okay, now by looking at the graph, like by assigning these colors, we can identify whether the graph is bipartite or not. So for example, if I take C3, what is C3? It is going to have three vertices, right? Now let me take edges here, right? This is C3. Now can you assign two different colors here so that no two adjacent vertices have the same color? See, if I assign, let's say if I assign red color here, right? Okay, then you may go with green color here, right? Don't say that you can go with blue color here, right? Because we are allowed to take only two colors, right? So here either I have to take green or red, right? So now we are not able to do that. Okay, now let us take another graph. Now let us take this example and randomly drawing. Okay, now is this graph bipartite? Now this is the graph G. This is the graph G. Is it bipartite? Now let us try to verify whether it is bipartite or not using this graph coloring. Okay, now let us color the vertices with red, and other one I am taking is green. These are the two colors I am taking. Okay, so this one I color with red. Alright, if this one is colored with red, then the vertices which are adjacent to it must be colored with green. Okay, so let me color this with green and this with green. Done. Next. So, and this one let me color with, okay, since these guys are colored green, now let me take the adjacent vertices and color with red. Okay, this one must be colored with red, yeah, and this one must be colored with red. So again you take this guy and here assign green color. Yeah, now I hope we are done. Now we can say that this graph is bipartite. Suppose if I name these vertices like A, B, C, D, E, F, right? A, B, C is in V1 and D, E, F is in V2. Okay. Now let me take another graph H. Mostly I'll do the same, but I'll create one extra edge. Yeah, now I'm not only just creating extra edge, I removed one edge also from the graph G. I removed one edge and I created one extra edge here. Okay, let me name these vertices as A, B, C, D, E, F, right? Now let me start coloring. Okay, the first one A, let me color with the red, and the adjacent vertices you color with green, right? Yeah, you're saying not bipartite. Okay, let us verify. So now since these are F is colored with green, adjacent guys must be colored red. And next, since this one is colored red and this one must be colored with green, yeah, whereas here it is colored with green and this one is must be colored with red. Now we are not able to do this because we are allowed to assign exactly one color, not that you can assign two colors here. Okay, so if I assign red color here, what happens? If I assign red color here, then adjacent vertices are having same color. Suppose if I assign green color here, then D and C are having same color, they are adjacent. Therefore, it is very clear that this graph is not bipartite. Okay, whereas this graph is bipartite. It is a bipartite graph. And there is one more theorem to know whether it is a bipartite graph or not. Okay, that is in terms of path. So what that theorem says is, if a graph is bipartite, okay, then you can start at one vertex and you cannot reach that vertex again by traveling via odd number of edges. For example, let us take this C3. Okay, let me name this as 1, 2, 3, the vertices. Okay, I am starting at 1. Now I traveled along the edge 1, next along edge 2, and next edge 3, and I reached 1. So how many edges we traveled here? Total 3. Okay, So now that is odd number and you reached 1. So this graph cannot be bipartite. And even the other way is also true. Suppose if it is not possible to start at a vertex and return to the vertex by traversing an odd number of distinct edges, then the graph is going to be bipartite. So if the graph is bipartite, then you cannot reach the vertex starting from the same vertex via odd number of edges. Okay, suppose if you are not able to get that path via odd number of edges, then it is going to be bipartite. Okay, so let's do one thing. Let us try to verify here. Suppose if I start at A, and now if I want to come back to A, how many edges I need to travel? Okay, let me go through it first. 1, and next 2. I'll go to C. Means let me write the path first. A to F, and then F to C. So for 2 edges we used, and then C to, okay, now C to E, and then E to B, and B to F, and then F to A. You see that how many we used? 1, 2, 3, 4, 5, 6. Now 6 edges we traversed. Okay, this is one path I have taken. You think about the other paths also, right? Not only for A, you start at any vertex. Suppose if you have a way to come back to that vertex, that way should take even number of edges, even number of distinct edges. Okay. So these two theorems will help us in identifying whether the graph is bipartite or not. Now let us come back to types of graphs. I hope we discussed 3 types: complete graph, and a cycle, and a wheel. These are the 3 types we discussed, and there is one more type. We call it as n cube. So let me define it now. N cube. So what is n cube? Simple. It looks like a cube. Okay, if it is in 3 dimension. In 2 dimension, that looks like a square. Okay, in 1 dimension, it's going to be a line. However, let me give the proper definition. So a cube is nothing but a graph with vertices representing the 2 power n bit strings of length n. You know what are bit strings of length n? Like it's an array of length n where the entries are 0 and 1 only. Okay, see here, if you look at length 1, that will have only 1 or 0, that's it. Okay, and now that graph we will denote like this. Like one vertex we assign 0, and another vertex will assign 1. Okay, so vertices of the graph is representing bit strings only in this case, and this is what we call q1. All right, now let me look at q2. So when it comes to q2, each vertex must be assigned either with 0 0, 0 1, 1 0, 1 1. Okay, there will be 4 vertices here. Now that we can easily construct like this. First you take bit string of length 1, q1. You take 2 copies of q1. Okay, I am having two copies of q1 here. Okay, now I will keep 0 before this bit string, right? And here I'll keep 1. Okay, now you connect the vertices for which the second entries are same. Right, now we got q2. Okay, here I explained the construction of q1 using construction of q2 using q1. Okay, similarly you can construct Q3 using Q2. If we say Q3, they must represent bit strings of this type. Okay, and there is one more thing. Whenever we represent graph like this, here, if the vertices are adjacent, then you look at the bit string, maximum they must differ by one digit only. For example, you see these two are adjacent, right? That is 1 0 and 1 1. Okay, so they differ by only one digit. Okay, and you see these two 1 0 and 0 1. Okay, they are not adjacent, and you can see that they are differing with what, 2 digits. If they are adjacent, definitely they must differ with only one digit. Anyway, now let me look at Q3, 3Q. So now here I'll take two copies of Q2. From that I'll construct Q3. So here is one copy of Q3, Q2. This is another copy. Okay. Now let us give names to these copies. 0 0, 0 1, 1 1, 1 0. Similarly 0 0, 0 1, 1 1, 1 0. Okay. Now you keep 0 here and here 1. Now you join it. Yeah. Now I hope you can see Q3. This is Q3. You can see that the adjoint vertices, they differ in exactly one bit position. Alright. Similarly, you can go think about construction of Q4, taking two copies of Q3. Okay, maybe you may come to the 3D space. You must go for the construction. Yeah. So I hope now you came to know what are complete graphs, what are cycles, what are wheels, and n cubes. Right. Now let me introduce one more type of graph, that is complete bipartite graph. We're going to discuss about complete bipartite graph. So the graph has to be bipartite, okay, and it has to be complete in one sense. Okay, if it is bipartite, it means there will be two set of vertices, V1 and V2. Okay, so let me, for time being, let me take V1 has 3 elements. Okay, the cardinality of V1 is 3, and the cardinality of V2 is 2, and total number of elements in V, these are 5. Now bipartite, it means you can find edge between a vertex in V1 and vertex in V2. That's it. Now we say that graph is bipartite, a complete bipartite, if every edge here, let's say you take in vertex in V1, this must be incident with all vertices in V2. I mean, so this must be incident with here. Okay, let me name it 1, 2, 3. This is 4, 5. So this has to be incident with 4 and also incident with 5. Okay, next to 2, it has to be incident with 4 and 5. And similarly 3 has to be incident with 4 and incident with 5. And we are going to denote this complete bipartite graph with this notation. In the first set there are 3 vertices, right? So we denote it as K3, comma. In the second set there are 2 vertices. Therefore it is K32. It means you take one vertex in V1 and another vertex in V2. You must have an edge between them. Okay. If you have an edge between 2 vertices, one is in V1, other is in V2. and if you take two vertices, one in V1, another in V2, there must be an edge between them. Can we denote K23? Yeah, if you denote K23, then in that case we draw picture like this. Okay, in that case we will say that V1 has two elements and V3 has three elements. That's it. You understand? So in that case the graph looks like this. You'll get the same graph, but it's going to be flipped. Okay, so this is K23. Alright. Generally whenever we draw, we suppose if you write 3 first, on top we will take 3 vertices, on down we will take the next vertices. Okay, I hope similarly you can think about K. Okay, you draw this, just K33. I hope this is how it looks like. First you connect like this, and similarly you take the other guy, connect it, and next this one. So this is what K33. Okay, so these are what complete bipartite graphs, and we denote with KMN. Okay, the general notation is KMN. It's a bipartite graph. In the first set there are m vertices. In the second set there are n vertices. Alright, I hope you understand what are complete bipartite graphs and also bipartite graphs, right?